Okay, let's try this. Here's my contribution for the Summer of All Zoom Epoch of Reionization Astronomy Conference, the sizes and morphometrics of high-redshift galaxies. I'm Ben Holwerda at the University of Louisville. My postdoc, Joanna Bridge, has done some of this work, and I've worked with this cast of characters here below. The underlying people are some of my students who've contributed to this. So finding high-redshift galaxies, traditionally we've done that through the Lyman break dropout. And so really what the information that we have are a few photometric detections in the near infrared and a non-detection in an optical band. And then we confirm those typically with Spitzer photometry. That is what Joanna has done for some of these Super 8s, these bright Redshift 8 candidate galaxies. And she reported on that in 2019. 7 new confirmed, and IRAC follow-up not only confirmed them, but in some cases we hope to get colors in the subsequent work. So Spitzer colors are great. The fact that H minus 3.6 is a good confirmation. However, if you use easy templates, for example, like you do here, you get a really wide range of IRAC colors, and not all of those templates might be appropriate for high redshift. So what else to use? You can use, for example, BPAS templates. These are more appropriate for high redshift because they're young, middle poor. And then if you run those through the 2 IRAC filters, then you see a completely different behavior, but much more similar. And you see this window between redshift 7 and 9, where there's a big peak in as H alpha moves through it. So what happens if I just dial H alpha all the way up to high? That's what Renske Smit pointed out to in 2013, and Guido Roberts-Bersani has used. And so what you do then is you actually run these really massive emission lines through it, and then you get this kind of behavior, and that really starts to explain the Spitzer colors that you see at like redshift 7 and 8. So that's much closer. So typically we think that these nebular lines are quite strong in these galaxies. So what happens with Spitzer photometry? We can, the 5th photometric point really, we can use it to confirm the photo Z's, but no new Spitzer data is forthcoming. Oh, too bad. So can size, effective radius in the HST images be a good alternative or supplemental constraint for high redshift candidate selection? Size is a useful confirmation value, and it might supplement or substitute for the H minus 3.6 color. So this is what we showed in 2015. So the recent work that I've done was on the brightest origin of reionization galaxies. So Morishita wrote a fantastic paper about that. And not only did I get to play with the actual selected sources, but also with the sources that he rejected. And so the visual inspection shows, that was my goal, to see where the visual inspection actually rejects sources, and if there's a way to supplement or substitute the visual inspection of these little high redshift sources. Color independent, but size seems to be instructive. So the green triangles here are the visually rejected sources, and so if you just put in a size cut, you actually take out most of the contamination, up to 75% of it, without having to do the visual inspection. So that was suggestive that an effective radius criteria could be a good substitute for a visual inspection. So what you do then, you take the curves that Charlotte Mason produced in 2015. These are the luminosity functions, and then you take your favorite luminosity size relation for high redshift. There's 2 of them that I'm aware of, the Graysian 2012 and my own from 2015, and then you convert that into a size function. And so that's what this has happened here. So the size functions are in kiloparsecs, and depending on which relation you prefer, then you get a distribution of sizes at a given redshift. So how many redshift sources do I expect to be above effective radius of 0.3 arcseconds? So that's what I've done here. So these are the two size relations. If I leave my own at redshift 9, then that's for bright sources only. They stay beyond below 0.3 just fine, and the variance is the variance here in the luminosity function translated as to the size function. So what I've done here is at the x-axis I've got the effective radius, and on the y-axis is simply all the galaxies that we have volume for at that redshift. And so if I use the Gratian size luminosity relation, there is some spillover if I go beyond 0.3 arcseconds. So you do have to assume the size luminosity relation in order to use a hard cutoff. But what you can do is simply say, well, beyond 0.3, I'll start tapering it off, because most likely these things are contaminants, and they're much less likely to be actual high redshift sources. So let's see what we can predict for future use. Let's assume my relationship is, hey, it's my talk. And so what fraction of high redshift sources would be spuriously rejected if I take a hard cut? And so this really becomes an issue beyond redshift 10. Well, actually, that's one that we're interested in for the shallow wide survey. So something like BoRG at redshift 9 and Euclid with the shallow wide survey. So using sizes of prior tapering between 0.3 and 0.5 arcseconds, that seems like a good way to go. Otherwise, you start rejecting a large fraction of the sources you're hoping to get. Other than that, most other surveys are perfectly fine, because they are both narrower, so they are not going to pick up as many of these bright sources, and they are going to pick up many more smaller sources, fainter sources, and then you can use this size cut with pretty much impunity. If I go to 0.5, really the problem only persists in BoRG beyond this redshift, and frankly, BoRG isn't going to get to that redshift. So really, I don't think we have much of a problem using size as a weak prior here. Another avenue that I explored with my student Samir Kushmich in 2019 is to see where the morphometrics. So morphometrics is a term that I'm using for all the parameters such as Gini, M20, asymmetry, concentration, etc., and to see where these bright sources actually end up in that parameter space. So the reason that I'm pointing this out is that in Gini-Asymmetry space, they all seem to be nicely clustered. These are the bright redshift 8 super 8 sources in both candles and in BoRG, and they all seem to be clustered close to the same, close to the values of Gini and asymmetry, and they don't seem to agree, or they don't seem to be close to what the PSF values are, what we expect for point sources. So that's looking promising, something that we want to explore a little further, but that is a nice research note by Samir. And I think both of these show some promise to be used as priors, as additional information to the photometry when we're searching wide surveys for high redshift sources. So the high redshift priors, they should be motivated prior for the galaxy sizes. So you should have assume a certain luminosity size relation. And I think you can use a morphometric prior for individual sources, and then replace the visual inspection because that becomes kind of impractical for something like Euclid or the Roman Space Telescope. And then, yeah, maybe these two might be good machine learning inputs. And so that's the next thing that I would like to explore. And so we can do a prior for size, and we combine that with a prior for morphometrics, and then we actually can use all the information if we want to get pre-select high redshift sources. Galaxy size, the actual sizes do constrain our galaxy evolution and formation models, so we do not want to bias ourselves here. But if we take the high redshift sources that we found, so for redshift 910 in BoRG, then the log normal distribution of effective radius that Shibuya found in 2015 for redshift 6 is still pretty representative. So that seems to be the distribution, size distribution of sources. It gets projected at different high redshift on the sky. So it gets projected differently. So my conclusions are the future applications of size and morphometrics in high redshift searches Our confirmations are sadly gone. We're still waiting for James Webb. And so the size can be a viable prior in our initial searches for high redshift sources. So especially for the wide, shallow stuff. Searches. Galaxy size is a good test of galaxy formation and evolution, so use a weak prior only, but it can definitely be a prior, and we should probably cut it off at half an arc seconds, because anything beyond that is definitely not a high redshift source. Morphometrics such as asymmetry and Gini look very promising, so I think the three of them combined in combination with photometry can actually be a good input for a machine learning approach. So yeah, below you'll see my Twitter and email, and please contact me if you find this interesting. Thank you so much.